In this lesson, we will look at another frequently used op amp based amplifier circuit. It is used widely in instrumentation applications and is aptly called the instrumentation amplifier. Okay. It is based on the non-inverting amplifier and it can be derived from that, but I am here just putting down the circuit. This has two op amps and you will be able to verify that each of them is in negative feedback. Okay. And let us say I have V1 and V2 at the two inputs. Again, this means that they are V1 and V2 with respect to some reference node. Okay. And I have these two node voltages at the as the outputs VO1 and VO2. In particular, the difference between these is considered to be the output VO, which is VO1 minus VO2. Okay. And the resistance values are chosen symmetrically. So, let us say this is R2, this is R2 and this one is R1. Okay. I will show the analysis with ideal op amps. If you want to see what happens with non-ideal op amps, that is op amps with a finite gain, then you can replace each of these op amps with voltage controlled voltage sources and carry out the analysis yourselves. Okay. Now, ideal op amp circuit analysis is very easy. I will use the virtual short between these two. There is negative feedback around each of these op amps that can be verified, as I mentioned earlier. So, the virtual short at the input of this op amp means that the voltage here is also V1 with respect to the reference node. Similarly, the virtual short at the inputs of this op amp means that the voltage difference between these two is 0 and this node voltage is V2 with respect to the reference node. So, this resistance R1, its upper terminal is connected to V1, the lower terminal to V2. So, the current flowing through this is V1 minus V2 divided by R1. Okay. And that current goes into this resistor, nothing goes into the op amp, and similarly goes into that resistor. Okay. So, the voltage drop across R2 is in this polarity this current times R2. Okay. It is V1 minus V2 by R1 times R2, and similarly across this R2 with this polarity we have V1 minus V2 by R1 times R2. Okay. Now, if you look at each of these voltages, VO1 will be V1 plus the voltage drop across R2. Okay. So, VO1 is V1 plus the voltage drop across R2, which is V1 minus V2 times R2 by R1. Okay. Similarly, VO2 will be V2 minus the voltage drop across this lower R2. These two resistors have to be of the same value. VO2 would be V2 minus V1 minus V2 times R2 by R1, which is also the same as V2 plus V2 minus V1 times R2 by R1. Okay. Now, what is special about this? I can also compute VO1 minus VO2. You can see that it is V1 minus V2 times 1 plus 2 times R2 by R1. So, we have V1 there and this V 2 gives you V 1 minus V 2, and we have V 1 minus V 2 times R 2 by R 1, V 1 minus V 2 times R 2 by R 1. So, we get 2 times R 2 by R 1. Okay. What is special about this? The point is, you can set this R 2 by R 1 ratio to be a large number. Then what happens is, even if you look at each of these outputs V O 1 and V O 2, a large part of that consists of the difference V 1 minus V 2. The individual voltage V 1 here is multiplied by a gain of 1, whereas the difference voltage V 1 minus V 2 is multiplied by R 2 by R 1. So, what it means is that it prefers the difference V 1 minus V 2 as opposed to V 1 or V 2 by itself. Okay. And if you take the difference between these two, V O 1 minus V O 2, you will find that it is proportional only to the difference. Okay. Now, why is this useful? This is useful, it turns out that many times you have to compute the difference between two large voltages, but the difference is small, but each of the voltages is large. Okay. So, let us say I have 15 volts, V 1 is 15 volts and V 2 is 15.01 volts. Okay. And I am interested in only the difference V 1 minus V 2, which is actually a very small number, which is minus 0.01 volts. Okay. I need a circuit that amplifies this very small difference and ignores the fact that each of these voltages is large. Okay. So, that is, it emphasizes the difference. So, what happens if I apply those two voltages to this circuit? So, let us say I have 15 volts and 15.01 volts. Now, here I will have 15 volts plus, let me assume that R 2 by R 1 is 100. Okay. So, I have 15 volts plus this is 100 and V 1 minus V 2 is minus 0.01 volts. Okay. So, I will have 15 volts plus this V 1 minus V 2 times R 2 by R 1, which is minus 1 volt. Okay. And similarly, here I have V 2, which is 15.01 volts plus V 2 minus V 1, which is 0.01 volts times R 2 by R 1, which is 100. So, I will have plus 1 volt. Okay. So, if I take the total, this is at 14 volts and this is at 16.01 volts. Okay. So, now the value of this circuit is very clear. We have two voltages with a very small difference between them. They have been amplified into two voltages with a much larger difference. We have 14 volts and 16.01 volts. Again, this is important in instrumentation applications where you are trying to sense difference between two quantities precisely. Each of those quantities can be large, but the difference can be small. So, what happens is that what is a very small difference 15 and 15.01, there is only 0.01 volt difference between these two, has been converted to two voltages which have 2.01 volts difference between these two. Okay. So, that is the value of this circuit. Is this clear? It is a very useful circuit and you will find that it is commonly used in instrumentation applications. To clearly recognize the value of the instrumentation amplifier, we can compare it with another structure based on non-inverting amplifiers, which also amplifies the difference by the same amount. This is the instrumentation amplifier. The inputs are V 1 and V 2 as we have seen. The difference output is V1 minus V2 times 2 times R2 by R1, and more importantly the individual outputs are V1 plus V1 minus V2 times R2 by R1, and the other one is V2 minus V1 minus V2 times R2 by R1. Okay. Now, if we have two input voltages, we can think of using two separate non-inverting amplifiers. I will replicate the exact same circuit on the other side. If we do this, what happens is the individual outputs will be V1 times 1 plus RA by RB. The other one will be V2 times 1 plus RA by RB, and the difference between them would be V1 minus V2 times 1 plus RA by RB. Now, it appears that if I set 1 plus RA by RB to be the same as 2 times R2 by R1, the difference output will be the same, but the important difference is in the individual outputs. Taking the same example values as before, if this is 15 volts and this is 15.01 volts, and we also say that R2 by R1 is 100. Okay. We saw that this would be 15 minus 0.01 times 100 or 14 volts, and this will be 16.01 volts. Okay. Now, the difference between these two is of course minus 2.01 volts. Okay. Now, if we do that in this case, let us say this is 15 volts, this is 15.01 volts, and I set this 1 plus RA by RB to be the same as 2 times R2 by R1, which is 200, because R2 by R1 is 100. So, this is 200, right. So, that means that the output should be 15 times 200, which is 300 volts. Okay. And this one will be 15.01 times 200, which is 302 volts. Okay. So, you can see that the difference output is minus 2.01 volts here and minus 2 volts over there, 300 minus 302, but the individual voltages are much higher in this case. In fact, this is completely impractical. If you have op amps with, let us say, 20 volt power supply, you cannot have a 300 volt output. This we will see later, but you can see that this 300 volts is too high and this 302 volts is also too high. Two separate amplifiers like this individually amplify V1 and V2, whereas an instrumentation amplifier like this does not amplify the individual voltages much. V1 comes out as it is, V2 comes out as it is. What gets amplified is only the difference. So, such property is known as common mode rejection. We will not go into that. You can refer to some book to get more details of that. The point is, individual voltages are not amplified, but their difference is, and that is the value of the instrumentation amplifier, which is required to sense small differences of two large voltages in many applications. Okay.